In this video, we will see another example of how to solve a linear system of equations by the elimination or linear combination method. In previous videos, we were able to either simply add the two equations together to eliminate a variable, or multiply one of the equations by -1 in order to have opposites of one of the terms with variables, so the variables would be eliminated. Looking at this example, however, we'll know that this is no longer the case. The x terms are not opposites. When we add them together, we won't get 0. And the same can be said of the y terms. This means that we're going to have to manipulate one or both of the equations before we can simply add them together to eliminate one of the variables. In this case, we won't be able to multiply simply by -1. We'll actually have to be a little bit more creative in what value that we choose to multiply by. If you take a look at the y terms, we'll notice that there's nothing we can multiply 3 by to make it the opposite of what would effectively be -4 if I were to change subtraction to addition by adding the opposite. And there's nothing we could multiply -4 by to make it the opposite of 3. So if we want to make the y's become eliminated, then we'll have to do a little bit more work than multiplying just one of the equations. Let's look at the x terms, though. Is there anything I could multiply 2x by to make it be the opposite of 4x? And here the answer is yes. I can multiply both expressions of this equation by -2. If I multiply both expressions of this equation by -2, this 2x will become -4x, which will make the x's become eliminated once we cancel. So, just like before, we should set up our elimination like this. We want to rewrite both of these equations, one on top of the other, off to the right. We need to distribute the -2 because there were terms in the left-hand expression. -2 times 2x. -2 times 2 is -4 times x plus -2 times 3y will be -6y. And in the right-hand expression, 16 times -2 is -32. And we can bring the second equation straight over. There's nothing that we have to do to manipulate that one. And now, we've successfully made the x terms opposites of each other, so that when we add these two equations, the x variable will be eliminated. Now, we can apply the strategy that we learned in the first video that we used when we used linear combinations to solve systems of linear equations. Simply add the two equations together, term by term. 4x plus -4x is 0. -6y plus -4y is -10y. -32 plus 12 is -20. And now I've eliminated the x, so the only variable I have left is the y variable. So I can multiply both expressions by the reciprocal of the coefficient, which is 1/10, in order to solve for y. This will leave me with, which is -1/10. This will leave me with y equals, negative times negative makes this positive. 20 divided by 10 is 2. So y equals 2. Since we're solving a system, we also have to find the x variable. So next, I need to find x. I can use either of the original equations, or even either of these equations, to find x. The first one has smaller coefficients. The next one has a smaller number over here. Both would be pretty easy to use. I'm just going to go ahead and use that first equation, 2x plus 3y equals 16. And I'm going to substitute in the value that I found for y in order to find x. So this is going to be 2x plus 3 times y. And remember that we found y to equal 2. And that'll equal 16. Simplify. 3 times 2 is 6. So this is 2x plus 6 equals 16. And now we need to get rid of all terms without our variable in it by adding the opposite. This will leave us with 2x equals 10. And now multiply by the reciprocal of the coefficient. This will leave us with x equals, and half of 10 is 5. So we've now found our x and our y, so we can put those together into a solution. 5, 2. So the point 5, 2 is the solution to this system of equations. As always, whenever you solve a system of equations, you can check by substituting 5 in for x and 2 in for y, simplifying both expressions in the equation and making sure that you get a true equation. And you can do that in both of the equations. You should get a true equation in each of them.